I'm going to show that for every positive integer of x, okay, the natural numbers is just another name for the positive integers. There is another positive integer such that each of these power towers is divisible by n. Now this technically isn't a power tower right here, but all of these guys right here are called, I've heard them called power towers. The base and all the exponents are the same value in this particular case. So let's get busy. Now, one thing that we can do very quickly, and this first step is actually, I guess, difficult because if you make this assignment, then x+1 is just 2n, right here. And so we have this term taken care of, right? But what about the rest of them? What does the 2n minus 1 work out? It turns out it does. Now, all of this is fairly obvious. This is a power tower, right? This is x raised to the x raised to the x. We're just using this assignment right here, which worked for the first term trivially, okay? So now right here, so the rest of the terms is what we're interested in. Notice that I've written down just the rest of these guys, all right? Now, so any one of these terms can be written as x, and I'll just write it generically, x raised to the p. Okay, and if you want to, I'll just come down here, call this p also. All right. So you see, each one of these terms is x raised to p, where p has to be odd based on this observation right here. Okay, that's kind of the crux of the whole thing. And then the very next line here is the binomial theorem. 2n minus 1 quantity raised to the p power plus 1 is really just this rewritten. Okay, it's just this rewritten with 2n minus 1 in place. You know, so in other words, it's each one of these terms, I guess, is a better way of saying it, okay? So each one of these terms is in this form, right? Each one of these terms is in this form because each one of these terms is x raised to ultimately some odd number, right? Okay, so when you do the binomial theorem, here's what you get, folks. P choose 1, notice, is the binomial coefficient. It's just a number which really doesn't matter. Now, if you'll take a look here, it's already dead on obvious that the result holds, because if you circle, let's see, just this part right here, let's go right here. And I'm just saving myself the trouble of having to rewrite this. If you want to call this k, then it's very clear that n divides k, or k is a multiple of n. You see this vertical bar, n divides k, is equivalent to saying that k is a multiple of n. Okay, so you see we finished with the problem because these two guys cancel. Minus 1 plus 1 cancel, and so it's QED time. All right, now let's work a concrete example just to make sure that you believe this. What if we had, let's say, 5 to the 5th power? Okay, 5 to the 5th power plus 1. Okay, we see that would imply, what did we make our n here? X is equal to 2n minus 1. So that would mean 5 is equal to 2 times 3 minus 1. 2 times 3, of course, is 6. 6 minus 1 is 5. Okay? So our magic number here is 3. And what we've just proven right here is that 3 should divide this number. Okay? Now this number is 3126. You guys can verify that if you want. 3125, I'll just write it out, okay, is equal to 3126. But notice, without having to do a computation here, remember the sum of the digits is congruent to 3, okay, mod 3. So you have, let's see, what do we got here? 3126, okay? Yeah, 3126. But notice that 3 divides this number because 3 divides the sum of these digits. Okay, let me write that. 3 divides the sum 3 plus 1 plus 2 plus 6. Right, folks, and of course that's 12, isn't it? 3 plus 1 is 4, and then 4 plus 8 is 12. So 3 divides that, and that's a well-known result from number theory. If 3 divides the sum of the digits, it divides the number itself, okay? So that checks off. Now, just the next one in the list would be this. And you guys, I won't work this out, but I had to do it with modular arithmetic, and it works out pretty quickly, actually. If you have 5 to the 5th, and then that is also to the 5th plus 1, okay? This is the same as 5 to the 125th plus 1. Now, what's cool about this, and you can probably see it right now, from a modular arithmetic point of view, mod 3, if you consider this mod 3, okay, you can reduce this exponent to 2 to the 25th, right? 2 to the 125th, I'm sorry, okay? And then you use the fact that 2 cubed is congruent to 1 mod 3. 2 cubed is congruent to 1 modulo 3 again. Okay, and then this would become congruent to, let's see here, 2 goes into 125, what, 62 times? 62 times? So you'd have 1 to the 62. Oh, wait, I got this backwards, I think. This is 2 cubed, right? 2 cubed is congruent to 1. So you would have to divide 3 into this. Sorry, folks. You would have to divide 3 into this. And yeah, I got that backwards. But anyway, this works out. Just you can verify this if you do laws of exponents on this. 2 cubed is congruent to 1. Divide it into this, and you get what? 41 with a remainder of 2. Okay, and you could see that it would work out nicely. You would get that this was divisible by 3. Okay. So anyway, take a look at that and verify that. But it's kind of neat. And then these numbers are so large, you're not going to be able to write down the Hindu Arabic version of this very easily. This already, you were lucky just to know that this was 3125. 5 raised to the 125th power is an unpronounceable number, an unusable number. But anyway, we proved it at this stage. We proved what we set out to prove. But playing around with these powers and treating them as just modular arithmetic problems is a fun endeavor all by itself. Okay. Good night.